before we talk about the keys, we need to introduce another important concept. It's called closure of FD sets. I think you have learned closure this concept in your discrete mathematics, and we also need to use the closures here to help us for both the FDs and the where attributes. Then what is a closure? So given a relation like R, as well as a set of FDs, we have a bunch of functional dependencies. We can represent as FDs into a set. Then we can check if a new FD F is logically implied by the existing FDs or not. And to answer this question, we can check whether this FDF is in the closure of the S. What does this mean? We can provide you with a concrete example. Let's assume we have a relation R. This R has a bunch of attributes A, B, C, G, H, I, and we have a bunch of existing FDs. We organize them into a S. The first FD we have is A implies B. The second one we have is A implies C. We have CG implies H, CG implies I, and B implies H. Then we have a question. Where A implies H to be logically implied by the existing FDs or not in a set S? Can we help answer this question and also prove it? So we can check maybe it is correct, right? Because according to the existing FDs, we have A implies B, and we also have a B implies H, right? And we can check, we can say A implies H based on the definition of FDs. And how can we prove this? Let me provide you with a proof formula. Okay, so based on the question, we want to provide a proof. And we want to prove that A implies H can be logically implied by the existing FDs we have in a set S. So the first one is, we know based on the definition we have A implies B, right? A implies B, and based on the definition we know, I hope you still remember what does this implies mean, right? We know if given any two tuples, if they agree on A, they will also agree on B, right? This A implies B is in the S set, and according to the definition, we know if we have any two data tuples, and if they agree on the A attribute, they will also agree with the B attribute, right? In the first part we can get. The second part is we have B implies H, and also based on the definition, right? We know given any two tuples, if they agree on B, they will also agree on H, right? And based on these two cases, we can derive or we can conclude that given any two tuples, if they agree on A, right, they will also agree on B, right? This is based on A implies B, right? And furthermore, they will also further agree on H, because we know that if they agree on B, they will also agree on H. This is based on B implies H, right? So by using both A implies B and B implies H, as with the best definition. Based on the definition, we can derive that given any two data tuples, if they agree on A, they will also agree on B, and we also agree on H. And we can say A implies H can be logically implied from the existing FD set S, right? So this is what we can prove. A implies H can be logically implied based on this S set. This S is a set of FDs we have already. So we can prove this based on the function, based on the definition of these FDs. Okay, let's come back to the slides. And this is one way to prove it. Another way to prove it is based on the closure of the S. So if we want to check if the F can be implied by S or not, we just need to check if this F is in the closure of S or not. For this example, we just need to compute the closure of S first, and then we can further check A implies H is inside the closure of S or not. What is the closure of the S set? It equals all the FDs which can be logically implied by S. It's a closure of functional dependencies based on the existing ones. The closure of FDs can be very useful. And then the question will be how to compute the S closure. If we use the definition of FDs, it can be very complex and time-consuming to derive all the FDs inside the closure, right? Because for each case, we may have to prove it by using the definitions. It can be too complicated. So therefore, instead we introduce a bunch of rules or axioms to help us. These axioms can be proved, and we can further use these axioms to help us compute the closures of FDs. We formally name these axioms as Armstrong's axioms. So Armstrong axioms have a bunch of rules, and the first rule we have is called Relativity Rule. Given a bunch of attributes in a relation A1 to AN, we can say these attributes implies a subset of A1 to AN. So this rule should be easy to derive and to prove based on the definition of this functional dependency, right? You can try to do this by yourself. It should be easy to prove it. And it is also very easy to understand. Given a bunch of attributes, we can derive or we can imply all the subsets of these existing attributes. Right? And the second one we have is called the Augmentation Rule. Given an existing FD, A1 to AN implies B1 to BM. Then we can augment both sides of this FD by adding C1 to CK on both the left-hand side and right-hand side. And we can get A1 to AN, C1 to CK implies B1 to BM, and C1 to CK. You can also prove this rule by using this definition of FDs. If they agree on A1 to AN, B1 to BM, and also agree on C1 to CK, they should also agree with B1 to BM, C1 to CK, right? You can prove this by using the definitions very easily. This rule can also be very useful, and we will show some cases by using this rule to help us derive some new FDs. And the third one we can use is called Relativity Rule. We have used this already in the previous example, right? What does this rule mean? Given a FD A1 to AN implies B1 to BM, and another FD B1 to BM implies C1 to CK, then we can derive a new FD A1 to AN implies C1 to CK. You can also prove this rule by the definition of FDs. If they agree with A1 to AN, we can say they also agree with B1 to BM, and according to this FD, we can also say they agree with C1 to CK. Therefore, we can derive A1 to AN implies C1 to CK, right? It should be easy to derive the definition of this new rule. Okay, so these are the three basic rules we can use in Armstrong's axioms. So with these axioms, we can derive the closure of FDs with an algorithm. So given an existing of FD of the set S, we can compute its closure by using these Armstrong's axioms iteratively. We assign this S closure equals to S based on existing FDs, and we have a loop. We try each FD inside this S, and we apply the reflexivity and augmentation rules in Armstrong's axioms to augment the S set. We can also add the new FDs to the closure of S. And for each pair of FDs in S, we can also apply the transitivity rule and to create some new rules to be added into the S closure. And we can keep updating the S closure until this closure doesn't change anymore. So in this way, we can calculate the closure of the FDs. Okay, this is about the closure of FDs based on the Armstrong's axioms. Actually, besides these basic rules in the Armstrong axioms, we can also derive some more complex rules.